Okay. Any other questions? All right, let me go over this code that I have so far. I'll post it to OnlineDB later, and then you can check it out. But the idea is this: I'm writing just like I think C++ 11 added in one's audited automatic memory management collection. So it's kind of the idea here is I'm doing it manually, so we can see. Right, the idea is here's this class, object class. So we're just going to go hold on to a reference to whatever object that was dynamically allocated, and we're just going to have a name field so that we can see what it is inside there. So every time we create an object dynamically, we'll just go ahead and tell the collector about it so it knows about the various objects via this add method. Pass in whatever object that we've created, and it's just going to maintain a list of those items. And then whenever it gets around to doing a garbage collection run, we would call the collect, which is just a stub because it's not actually going to go through logic. The idea is to try to give you an idea of what may or may not exist at any point in time when we're dealing with our dynamic memory. Right, so I was last working on the tree part, building up a tree. So at the moment we have just a method that happens to be creating a list of stuff. Every item that gets created then ends up being added to our garbage collector. And then after this method is completed, only reference that we had to those list of items is within this local variable items. So if we do a collection while we're on the stack here, then nothing will be lost that was created here because we still have access to those items via this root object. But when we come back down here and do a collection again, that collection would cause all of these list items to go away because the root object items would no longer be accessible, right? Because when we leave that stack frame of build list, that goes away. It's kind of the idea. Let's see if we find use for not when I complete the task. Okay. Let's do some more Huffman codes. All right, so depending on the data, the number of symbols, we will get given trees. So go ahead and get 6 in here. And see what we get. As a result. All right, so if we can remember last time, first step is to create the forest, then we'll sort the forest. So we'll just do that as 2 steps in one. And I'm going to skip including the letters in it. I'll just put the numbers. Can't sync my changes, okay? Someone's hacking Google. All right, let's try that again. All right, so we have 9, which is D. As our table to the right shows. Let's see, is that going to be big enough to hold 2? No, it's not. All right. All right, so 9 is our lowest count at D. Then we have F with 12. C has 17. 27 for A, 31 for B, and 40 for E. All right, initial state, sorted forest. Go ahead and grab 2 nodes from the forest. Oops. Combine them together. All right, smaller one will be on the left-hand side, larger on the right-hand side. Combine them together, create a larger tree, and then reinsert that into the list. All right, so those have been combined. When we bring it back into the forest, we bring back into sorted order. And we have 1 fewer trees. Repeat the process. Grab the 2 smallest trees. Combine them together. And keep on going. Rinse, repeat till we are done with the forest. Get that down to just a single element. It's 38 typo for 31. We're no, 31's B. But I did put these in the wrong order, so let me put that. Thank you for asking the question because I couldn't sort, apparently. There we go, sorted. Okay, we'll take the smaller 2 nodes, combine those together, and then drop it back into the forest. And I'll say that a couple more times. Bring it down to 3 nodes in our forest here. All right, smallest two trees grabbed, then combined. If there happens to be duplicate values, right, same as other scenarios, the first value you grab is the left one, the second value that you grab will be the right one. If that circumstance were to occur. Down to our two trees. Which we'll just go ahead and combine together. And assuming my math's all good, we're up to 136. All right, now that the tree is built, just go ahead and add back in our symbols based off the table. Because the symbols didn't much matter for the building process, I just skipped that at the beginning. It was 12F. Of course, if I have duplicate symbols, I have to be careful not to make a mistake by doing that. By the way, here's our symbols, and then we had our left-right pattern. All right, zeros go to the left. And then our ones will go to the right. For the generation of our code words. Okay, so our path. Right, the path to get to A is going to be 0, 0. The path to get to B will be 0, 1. Path to get to C will be 1, 0, 0. 1, 0, 0. Path to D, go through 1, go through 0, go through 1, go through 0. 1, 0, 1, 0. Path to E is 1, 1. And the path to F, 1, 0, 1, 1. So we can go ahead and update our table accordingly. Let's grab our given part, and then we can fill in our code words. All right, remember these are the bits that we're using instead of using a basic or a standard symbol table. And the footprint, if I can spell and or type, and just the number of total bits that's going to be required to encode every occurrences of each symbol, right? So 27 occurrences of A. Each code word is 2 bits long. So we're looking at 54 bits. Here we have 62. That's 51. If my brain's working, 36. Always good to check my math. And 48. So our total encoded size would then be the sum, the last column. Yeah, let's get the calculator on that one. Feels the odds of letting the brain try to do that works too much. 8. Let's check the calculator. Okay, typos. All right, 331. All right, so original size. We have 136 symbols. 8 bits per symbol. All right, 136 times 8, 14. No, let's try that again. 136 times 8, 1088. It's original payload. So what is our compression rate? Please do the math and then post the number and then we'll confirm. Everyone found their calculator? There we go. We got one. It's a number. I don't know the number yet. I haven't done the math myself. But if several people start to agree with you, then odds are that will be the number. We'll see if 69 is it. Looks reasonable based on those two numbers. Seems we have a confirmation, so let's double check. Original size minus compressed divided by original size. Looks like 69%, 69.6 if we're going to a decimal point. 69.6%. And here I am typing it in the chat instead of over here. All right, so we should know where this number comes from based on these two data points and previous notes. All right. So which bit of this do we want additional clarity on, or do we want to do again another build? All right, so one of the key things that Huffman code when we built this system was the prefix clause. None of the code words that are in this table are a prefix for any of the other code words, right? So A's code word is 00. So you won't see any other code words that have 00 as the first two digits. Same thing for 01, right? No one else starts with 01. By having that in the scheme, we don't have to do what's called look ahead on the read, right? So if we had, there's an annotate, we are, if we did have that, say we had, right, P. Code word for P is 0 and code word for Q is 1. Right, so if our input stream is 0, 1, 0, 1, is that a PQ, PQ, or is that going to be, was 0, 1, is that a B again? Yeah, B, or is that a BB? Right, it creates a complicated situation for trying to decode what that value is based off of the data and the reuse of the prefixes. Right, so you could have an encoding scheme that does do this. And one encoding scheme that does do that is Morse code. Right, which is a binary system where we have short and long, but there is actually a ternary pattern because there's pauses, right? So, for example, dot, E is a dot, I is a double dot, H is 4 dots, right? So if we have 4 dots on the input stream, the way that we differentiate that being a single H character as opposed to 2 I's or an E, an I, and 2 E's is by having a pause. So if you get dot, 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 that's 4 E's. If you get dot, 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 right, that's 1 H type thing. And so by having a pause, that's just an extra bit of data that has to be transmitted across the wire. Of course, when Morse code was done, that's by just putting spaces in time. The Canvas grade, we can check that later, Mark. You can do screen sharing, or you can send me a screenshot, or it should be taking that account. In fact, let me just do a test, assign some grades to the test student. We can show it. So it's also applying the rules, right? So the lowest test score is dropped already. You can always double check them. We'll get an Excel sheet going over later, and we can double check that the calculations are in fact accurate. Right, so you can see with Morse code, right, you can see have variable length code words where E is 1 and T is 1, where one's a dot, one's a dash. And when Morse developed the code words, you can see like letters like Z, Y, X, V, right, where's Q, J, letters that were identified as being less frequent than others were made longer code words because that way you can get the message across faster because it requires less time on the wire, right? To say Bob is hungry as opposed to, just listening at radio stations. It's WPQR or whatever type thing. If we're just going through all the radio stations in the country, then that set of data would not work very well with Morse code because it happens to be using all the letters that are encoded as 3 or 4 long, whereas more common pattern is to have them shorter. Right, so one of the things you could do based off of your system, if you have a system where you have common sets of data, common patterns in the data, where you can just go ahead and one time build your quote unquote standard Huffman table, where it just creates one table based off of the common pattern and frequent occurrence of the letters, the symbols, and then develop the code words. And then in the metadata of the message, you say this, we're using this standard table or standard table 4, or here is the actual table that we built for this particular set of data. Right, so the Huffman codes are going to be variable based off of the actual data itself. And then of course, systems at scale might look for opportunities to help streamline that, right? Because if we're frequently generating a set of data and then compressing it and then sending it, and then it needs to be decompressed, and it's possible you might even be sending the exact same data to someone else. We have multiple clients in the system, and they're sending that data to them. This is where creating a standard, right? Not necessarily an industry standard, but a standard within inside your system itself for what custom tables are. That way you can just go ahead and submit the custom tables, right? Just like for a long time, everyone only ever had ASCII on their computer. Right when Unicode was first out, a lot of systems wouldn't support Unicode. In fact, there's still one of those problems with GitHub. You try to create a non-UTF-8 code file and upload it, and it says, I can't show you the diff because I don't understand the symbol set of this file. So there's still even some systems that are still fixed to the 8-bit structure, right? You know, C as a char is an 8-bit character, right? You have to go to a wchar if you want to support Unicode. So even though Unicode's been around for a good long while, there's still several ways to skin the cat, as it were. Called dits and das, 3 times as long. All right. How are we doing with Huffman? Do we want to do another example? Or do we think we have a good handle on it? All right, more examples. The 69% is from our compression rate formula. It's the size of the input minus the size of the output divided by the size of the input. All right, so it's good. So we got 1088 minus 31 divided by 1088. And that gives you 69.6%. New topics, I'm adding additional details to our existing topics, but there shouldn't be any new areas. All right, Mark, I'll check that out on our break. Okay, so let's change the numbers. Let's force duplicate values as well while we're here. So I'll give us some duplicates. 35, 25. And let's see, who is that going to get there? 55. We'll see what we get. Get a new screenshot. All right, time to draw. All right. Okay, so since I do have duplicates, I will put the letters in here as well. So we have A and C both at 15. E at 25. Where are we now? 30 for B. 35 for D and 55 for F. I just won't bother repeating. All right, so we grabbed the first two. Grab those two. Coloring scheme, combine those together. And since A was first in the list, it ended up being on the left-hand side to create our 30. All right, and now we need to reinsert this into our list. Where we already have a 30. All right, so make space in front of the first 30. And we'll drop it in there. And then repeat the process. Grabbing first two trees and combining those together. Getting us a bit larger. Larger, taller, whichever way you want to look at it. Keep killing my caps lock. All right. All right, and the 55 gets reinserted into the tree in sorted order. All right, so we just start at the beginning more or less. And we'll iterate down until we find the appropriate spot to input the data. All right, so we'll grab the first two as we have before. And real estate, so let's get another slide going. All right, so we grab 30 and 35, combine them together for 65. And that gets reinserted into the forest. And we'll keep chugging along. Grab our first two values from the forest, repeat. And then that'll get reinserted. Once we splice these together. 55, 55, all right, so we got 110. I'm just gonna keep it short here and just put 110 because there's only going to be one of those. All right, and then last step, combine the last two trees. Giving us our code tree. Oops. Skip a step and then things don't work out so well. All right, so 0101. So our code word for B will be 00. Code word for D will be 01. Code word for E. We went right, gives us a 1, 0, 0. Code word for A, right, give us a 1, 0, 1, 0. And then C will be the same, except for that last digit will be a 1. And then we have F as a 1, 1. Went right, right. Right branches get the 1s, left branches get the 0s. And our symbol table is built, so it's just a matter of dropping these back in. Leg, let's try that again. All right, get to our table. I'll let you all work on calculating the footprint. Based off these code words, you can just post it in Discord later. Okay, E is 100, A is 1010, 11, and F is 11. All right, so grab that table, populate it, drop in Discord, and people can see if we're in agreement or not, or if we need to tweak what you're finding over in that area. Questions about, yeah, general tab's fine. What number are we on? Oh yes, Hamming code. All right, so before we get to that, let's make sure we're on a good foundation for parity. All right, so using 5 data bits. That doesn't work out too well. And that seems good enough. All right. Let's remember the convention we're using is even parity. We're only doing even parity because the even parity is the de facto standard. So when we're looking at our first chunk of data. Count how many on bits there are. We have 3 on bits. So to get our parity, our total number of on bits to be even, we need to set the parity bit to 1. Now we have 4 on bits and good to go. Keep on going. 5 on bits, set that to 1 to make the parity even. All right, 3 on bits again. So we set the parity even. Just hold on. I miscounted earlier. That's a 0. There are 6 data bits. All right, 5 data bits on. Set the parity to 1. 5 data bits all off. Set a parity to 0. All right, so any given row, we count how many on bits there are. We will have an even number. 0 in the last one. 2, 6 over. Nope, not there. 6 over here. All right, and 6 is as many on bits as we can have when we have a total of 7 bits in the payload. All right, so depending on data bits, right, using 1 data bit, right, the trivial case. Yeah, 0, the parity, so the data can either be 0 or 1. And if the parity is already even, we keep the parity bit off. If the parity is odd, we set the parity bit on to get our total parity to be even. All right, so what's the parity going to be for this data set where D0, D1, D2 are all zeros? Seems 0 is a popular answer. All right. The second data set, 1, 0, 0, what's our parity? Toggle over to ones. I don't know if that last 0 is from the first data set or not. Looks like 1. That's a funny looking one. All right, we set a parity to 1. Our total number of on bits in the row is now even. Next data set, 1, 0, 1. What shall we set our parity to? Third data set. Yep, third data set. 9, 0, yeah, almost there, right? I've got 1 vote for a 0. Are we in agreement? Do we want to set the highlighted cell to a 0 or do we want to set that to a 1? Got a direct vote for 0, public vote for 0. That's 3 in agreements to each other based on a repetition rule. That looks like we're good there. And the last possibility with 3 data bits is to have 3 data bits set on. And it looks like we're already jumping to the answer, which would then be 1 to give us our even parity. All right. So our Hamming code. Get this link open. Okay, I didn't mean to copy it, I meant to open it. All right. Grab this big old table. The table is very useful for seeing how the Hamming code works. All right, so for this table, all right, following table shows a 20-bit payload. This is inclusive of data bits, which would be DX, and parity bits, which are the PX, or just call them PY, whatever. How does parity for hex numbers work? Well, hex is just a 4-bit binary value. So if you wanted to transmit hex data and you wanted to add parity, you would have a 5-bit payload. So you would have 4 bits for each character. And then you would set the parity bit based off of that character's parity. All right, so half the characters would already have even parity and the other half would have odd parity because it's got all the permutations of 4 bits for 0 through F. So half of them you would set the parity bit on, and the other half you would just leave it at 0. All right, so in this table, so the first 2 columns are parity bits. Same is true for column 4, 8, and 16. So in all, we're talking about columns 1, 2, 4, 8, and 16. Notice a nice base 2 growth pattern. All right, so parity here is the same as we've seen elsewhere, except we're not setting parity for the 15 data bits based on the entire set of those 15 bits, but rather subsets of those 15 bits, and doing so for each parity. Okay, so let's see, 20. Good. So I'm just gonna go ahead and shrink my font so I can get that to fit. Yeah, that's probably fine. All right. Parity to D1. Oops. D2, D3, D4. And we're up to parity 4. Yeah, I guess I'll keep it consistent with how they have this here. They're saying P4 instead of the third parity. That's fine. Parity 8. All right, where are we? D5 through 11, D5, D6. Typing challenged. Let's see how far we gotta shrink to get that to fit. All right, down to 11. Okay, 11. And we've got parity 16 and so on. And of course, it's automatically capitalizing for me. It's so helpful. So helpful. Sometimes help's not all that it's cracked up to be, right? All right. Yeah. It's always funny when the application you're using is trying to be more intelligent than you, and sometimes it reads into things that aren't actually there. All right, so if our data, let's do 4 zeros, 4 ones, 0 1, 1 0 1 0, and then what are we at there? 14, one last data bit. So our data is the given, 4 zeros, 4 ones, then we have 0 1, 0 1, and I goofed up somewhere. Where did I goof up? 4 4. Oh, I've got 17 bits here. That'd be my problem. Let's shrink that down a little. All right, and then 101. 101. All right, so here's our initial data state that we want to ship in the payload. And then we want to set the parity. Right, so we want to set this bit based off of every other position. So it's only the data points that are in every other position that we care about when setting our parity. So we have 2, 4, 6, 8, 9 bits that we want to set parity on. So we just go through these 9 bits. 3 of them are on. So we'll go ahead and set. Right, we set this parity bit based off of these values. And we'll do the same thing, setting the parity bit for 2. Right, that wants to look at data 1, skip 2, and look at these. Skip 2, look at 2, skip 2, look at 2, skip 2, look at 2, skip. We're at the end, so we can stop. So to set the parity here, look at these data bits. We have 3, 4 on bits, so our parity is set to 0. Yep. And we continue along, right? So parity 4 wants to get set based off of first set of 4 values. Grab, right? So it's grabbing itself inclusive in the count. So grab 4, including itself, skip 4, grab 4, skip 4, grab 4 right at the end, so we stop. 3 on bits. So we'll set the parity to 1. And then same idea, now we're just grabbing 8. Inclusive of the parity bits, we'll grab these 7. And then we will skip a whole bunch. And then we can set our parity based off that. 5 bits are on. All right, no, I thought that was bullet already. Okay. And then our last parity bit, this one here, right? Grabs all the remaining data, and we'll set that parity bit on. Right, so we can just drag down all the bits. And that will be the actual payload. That we would send for this given data. Right, so we have 15 data bits, 5 parity bits. We have a 33% overhead on the payload, but we are going to be far more resilient to data errors getting biased because of the redundant capture. Right? If we change so a single parity bit suffered from even flips. So if we were to flip these 2 cells, Where's my fill color? Highlight. All right, so if we go ahead and introduce some error here, and then check, see if the parity is good. Know if an error was detected. Right, so these 2 bits we're saying got flipped in the data stream. So all I have to do is check our parity. All right, so the first parity bit says we're okay. Right, in fact, let me just go ahead and get this everywhere because the columns are all the same, representing the same point of data. Right, first parity bit still passes. We have 1, 2, 3, 4, 5 data bits on, so the parity bits being set to 1 is lining up. We can see over here in the next 2 rows, the even number of bit flips now becoming an odd number of bit flips for both of these parity bits. So both of these parity bits are going to report that we have a data error. Right, so if we try to do same thing somewhere else, try to do an even set of bit flips. All right, we'll do different set of even bits being flipped. All right, so let's say we'll grab these 2 bits. We'll go ahead and see that those got corrupted. We can check our parity. All right, so here we can see this parity reports a failure. This one gets slipped through because they're both inside our data set. This one also slips through, oops. But someone caught it, right? Someone catches our errors. That's the idea of the overlapping. So by having overlapping coverage, it becomes much less likely for data error to go undetected. Obviously, there's the potential for enough corruption that it will go through by toggling a bunch of bits, right? Because there are, of the 20-bit payload that we're going to be passing, there are other possible combinations of data that can result. It just becomes mathematically far lower chance than it was before. Right, so for the final, you will not be memorizing this table. Right, I would be go so far as to give you the table for the final. The important thing here is this is a parity-based system, just like RAID's a parity-based system, and parity bits is a commonly used concept in various places in computer science. So knowing parity is something you should know. The application of parity is done in many places. And if you want to, if you like error detection and correction, let's see, check. All right, this is another one. Let's see how good this website is. It's not in our, it's not what we want. All right, text errors, accidental changes, and it's more math on the data, just like we're effectively doing with parity, we're just even odd. If you are an area that interests you, error detection. Check out CRC. Right, CRC is used in the network layer. Last I checked. Let's see if it still talks about that. All right, our TCP/IP stack, TCP. No, it's not talking about whatever. All right, you take a networking class, you guys can delve deeper into that one. So I'll just leave that as a little breadcrumb. No, there are no CRC check questions on the final. Right. Test it on. Let's see. Any questions about repetition? Let me just swing through. Our data compression, custom symbol tables, custom codes, all that's fun. Data compression, data integrity. RAID, which is a big fan of parity. I think that covers it. All right, let's go ahead and we'll take 5 minutes. And we'll swing over to the practice test, see how things are going there. All right. Shift folding. And so we have the first three. Doesn't use the cube. All right, 698 plus 741 plus 253, 1692. Which of these gives us a perfect yield? Okay, so we'll do divide modulo, and we have modulo plus divide, and we have modulo minus divide. And let's get a column here. So we have 6. 6 divided by 10 is 0. 6 modulo 10 is 6. So modulo plus is going to give us a 6, and then 0, 6. Let me flip my table around here so I don't goof up. My math, we have 32. And 32 gives us 3 and 2. So 3 plus 2 is 5. 3 minus 2 is 1. 33 gives us 3 and 3. All right, so we can, at this point, we now have a collision for modulo. So modulo is eliminated. Gives us a 6 here, and this one's also eliminated. We have 2 6s and a 0. We go to 44. Don't care about that one because it's been eliminated. It gives us a 4. Now we didn't care about that one because it was already eliminated, and that gives us a 0. All right, so division gives us a perfect hash. Excuse me. Get back to my mouse. 30%. Oh, I got my things backwards. Thank you. Switch the table around. And then goof this up. Okay, let's see if I can fix that. Let's try that again. Oh, there goes the whole thing. Fun. Yes, I got that backwards. Sorry. In which case the answer is no longer. All right, well, I guess we're doing that again. Let's do that one more time. Value modulo divide modulo plus divide and percent minus divide. 6, 6, and 0 gives us 6 and 6. 32 modulus 2 and 3. And then adding and then subtracting gives us 5, 1, which is actually 9 because of wraparound. 33 is 3 and a 3, so we eliminated divides. My answer is obviously wrong. 6 and 0, and then 44. Modulo gives us a 4. Divide gives us a 4. 8 and 0. Okay. Before I click away, let's double check my math. Is my math all right? Someone else catch me goofing up here. Okay. So modulo is our perfect hash. Everyone's good about the wraparound, or just like when we do a linear probe, we try to go beyond the end of the table. For too large, we wrap around the beginning. Same thing, the reverse is also true. When we try to wrap around below the end of the table, we wrap to the other side. Okay. Right, same question, different numbers. Right, and we'll just approach this one this time, one by one until we can eliminate. All right, so modulo 6, still good. Still good, and then we get down to the end and this one fails, so let's try divide. Right, so this one's gonna fail at the end as well. Falls down at 7. All right, so let's go further. Additive, 6, 7, 8, and then 13, which is really 3. That one's perfect. This one won't have to go to the next one, but we'll do the next one for completeness anyways. 6, -1, which is 9. -6. Let's see. Range 5 less, that should be 4. And we're there, -1 again. 9, so that collides, right? So addition is the winner this time around. All right, 40 wants to go to 2. There's a collision, linear probing. So we're going to go ahead and just go to 3. 60 goes to 6. Again, linear probing. Wrap around, collision, collision goes to 2. Reference counting. Okay. So objects. Refs, aka the count. First object is C, X keeping track of it. Now we have Y tracking it. Then object B comes around. Y jumps over. Oops. Then we say X equals Y. At which point C goes away. So after X equals Y, causing our reclamation. Any questions on number 6 before we carry on? All right, sliding down, tricolor. So we'll have our 3 sets. Black, gray, white. Let's go ahead and put A and G. Gray set to start, and then everybody else. C, D, E, F, H in the white set. So we want to move A out. To do so, B and C will have to be pulled out of the white set. Then we want to pull G out. G has no one in the white sets. We're done there. Pull B out. B has no one in the white set. So we're also done. H, B, C. C has E. Pull that out. Forgot to pull E. E has no one. So it leaves us DFH as garbage. D, F, and H. Well, the roots are going to be given to you. Otherwise, you won't know what you can trace from. So you have to be given the roots so you can do the tracing. Any questions on other questions on number 7? Okay. Hash table class, right? So we'll have, of course, naming can be somewhat arbitrary, but we'll have a lookup, we'll have a hash function, we'll have an add function, probably have a delete function, probe function. Quadratic probing in the test? Yeah, there could be quadratic probing. All right, so our lookup applies the hash, finds the data. All right, this is the math for our hash function. Add, applies the hash, drops the data in. Delete, finds and removes and addresses the holes that might exist as a result. And probing is dealing with our collision resolution. Depending on our type of hash table, right? It might be a linear probe, quadratic probe, chain, any of that might be the case. Let's see. If I goofed on anything that you guys didn't catch me on. Looks like I got everything. So the last point is not graded. I thought it's going to be. All right, so if we do boundary folding instead of shift folding, then the numbers 7, 4, 1 would have been flipped. We flip the even boundaries. Number 6, am I expecting all functions? Number 6. That number 7. Okay. Number 7, we mean number 8. All right. Yeah, you want to be familiar with our hash code. Hashing is pretty much like half the test. So you want to make sure that you're familiar with hash functions, hash values, our collision resolution, the hash table, table code. Yeah, and lookup is funnily the whole purpose. That's the one we want to see hit often. All right, when we delete from hash table, let's, all right, so we have this table, and we have 4 and 14, both wanting to go to this position. All right, so the first one in gets to be in the ideal spot, and then 14 collides. If we delete 4 later, and we create a hole there, 14 might get lost if we don't do something about that, right? So one of the solutions we talked about was to collapse the chain, which is the ideal solution because that improves the lookup. The other one was by, marking the position as formerly occupied, so that on lookup, we should treat the value as the value that's actually there. We just look at the value. But note the flag type thing. Well, you can actually look at the value. We probably do want to mem set it to 0, otherwise lookup form will be like, hey, yeah, it's still here. Yeah, so we need to actually make it a hole by limiting the value, but we can't just have whatever our empty value is, right? Say -1 is our empty value because it could affect the lookup of 14. So we either need to flag the cell as formerly occupied. So if a new value does come in, right, 7 comes in, it could just overwrite the contents and no longer be a formerly occupied situation. Rather than occupied, and then we find 14 where we find 14. Collapsing is programmatically more complex, but is of greater benefit to the lookups, and we expect there to be more lookups than adds and deletes combined. So the lookup function is usually the one that we want to make sure everyone else is doing their best so that that one is optimized. Just our best actual performance. Yep, test is next week, and then the final is the week after. We have 2 more meetings past today, and then it's over for this class. I think if you have Tuesday or Wednesday classes, you still have 2 more days. Definitely running up. To the edge of the holiday. Oh no, Tuesday is 22 is a purple day, so that should be off. Class 9, yeah, so almost the very last class. Right, we had some Monday holiday earlier in the year, so I'm guessing that's why they had Monday, Tuesday go all the way to the week of the 20th. Can't say. It's like Thursday got hit pretty hard this semester. Anyways, when does spring start? It's green. That's factually weak professional development. Yeah, okay. So while we're here, grades are probably due around here. I haven't seen an email about it yet, or I've already filed it away and forgotten what they said. So late work will be accepted till January 2nd. So if you're late on anything, obviously, as usual, the sooner you turn in, the lower the late penalty. So you don't want to wait too long. But of course, we're writing up right on top of the holiday. I can see people not using that time to catch up on late work. So yeah, late work, try to catch up on it now before the final week. There we go. Before the final, so you can go ahead and get that turned in. Yeah, we'll review for the final next week. So next week is take test 5, go over test 5, or review for the final and go over test 5, whatever those two project review for the final, then go over test 5. Some people have extended time, so I don't want to overlap. On top of that, you have to turn in the work to get points. So at the end of the semester, when the second rolls around, I'll apply zeros to everything that's not turned in. But you can still get at least 25% credit for anything that's turned in late, even if it's the very first assignment. The floor for 75% is the max for the late penalty. So anything that's missing, you can still turn in for points. Let's see. Program 4. No, we're not using reverse blush for program 4. It's just regular infix notation. The start and finish for program 4 is just to establish scope. All right, so let's what's my numbering convention for programs? Programs 0 dots. Okay, 0. Verb 4. All right, so let's do a sample program and then confirm the logic for x equals 4. All right, so create variable object. Name x value 4. Scope is 0. And to hash table. All right, so I guess we can do a drawing here. All right, x 4 0. Our object state. So that's present state of our hash table. All right, next line of code, var y equals 10. And we'll assume no collision at this point. So we'll just do a separate row. Let's put it up there. It's y. It's 10. Guess I should use colons instead of dashes so we don't confuse negative values. Start. Scope level of objects. Created is now 1. So we can say var z if we wanted just someone entirely separate equals 9. And there's a 67% chance of probability. So let's try on this. Unable to create some drawings. Yeah, I noticed. Something went wrong. Indeed. Reminds me, I was in Paris the first time I saw Chrome crash. And I was freaking out thinking someone hacked the hotel Wi-Fi. I was like, because Google and their error messages. They like to be clever. That's for sure. Okay. So I'm going to assume Z. Now it's scope 1. Ended up in the second list. All right. C9 scope is 1. Yeah, such a small table. Collisions are probable. That's so small. That's why, because they got whiter. Okay. So if we say print Z, okay, that outputs 9. We say print X, that outputs 4. And then we come along to a finished block. Let's do some more. Let's do var y equals 50. Since we're inside a subscope, we are allowed to use the same variable name again, not that we're actually enforcing that sort of thing. If they say var, we create it, we drop it in, and it's good to go. Be a little bit weird if they say var x twice in the same scope, but whatever. All right, whatever, create the value as 50. All right, so we're still in the nested scope. So 50 comes along, scope 1. And so if we come along and say print y, the output's 50. All right, we go to the ends up being the first list. We find y, that's a match, and we print it out. No, they would not replace. If I were to say, if we just say x equals 20, right, we just do a modification. We'll hash x, find who goes to second list, see that z is not x, we'll go past it. And we'll see x is over here, and we'll change the state from 4 to 20. And now we'll go ahead and hit our finish. So scope 1 is being destroyed, and the scope becomes 0. Excuse me. All right, so now scope 1's being destroyed. So you go to each list and you tell it to purge any node that says it belongs to scope 1. So that first item goes away. And same thing over here, that goes away. Yeah, keep killing my arrow. And let's just redraw, okay. All right, so that scope goes away. So if we were to say, second. There, okay, so if we go ahead and say print X, all right, we get 20, we say print Y, get 10. If we say print Z, we say that does not exist. Can't print it. This is assuming you're using a single table for all your variables. All right, the other approach some people take is they create another hash table. So they have an array of tables. When the scope goes up, they start in scopes table first, then you do a lookup there, and then you go down to the lower table and you do a lookup there, and then you go to the lower table, lookup there. It's not going to be as efficient because now you have to iterate through all of the tables. So I'm not going to draw that out because I'm not going to encourage you to go in that direction. If you're in that direction, that's fine. It's certainly easier to handle scope that way, but it's at a detriment to your lookup, which, as we were talking about earlier, if it's a detriment to the lookup, that's the opposite direction that we want to go in. Because when we do, right, say we created 4 more scopes from this point, right? Let me just say start. Ooh, start, and then we say var z, and then we say print x. Doing the other way, now we have, you're looking in this table, then you're looking at this table, then you're looking at this table, then you're looking at the scope 0 table, which some people have been calling global variables, right? It's just scope 0. It's, yeah, kind of like a global variable with our primitive language here. With this one, I say print x, we hash goes as lists for element. There, it's as fast as it possibly could be with the one table approach, assuming z ended up in list 1 or list 3. All right, so let's say I do have this code. Might as well put the state while we're here. And I'm just going to go ahead and put z over here, give it a value 5, and go, we're at scope 3 now, and 3 starts, right? Yeah, so var z equals 5. All right, so we'll look up to z, constant time, x is constant time, and y constant time. So if we wanted to print any of these, x, y, and z, all in scope right now. X is presently 20, y is presently 10, and z is 5. Okay, other questions? Output, just run application and generate the output right here. Like, you know, it's X is 20 is the official format of the output type thing. Extra credit is adding language capabilities to the Borg language. Why is Gandalf undefined? All right, let's grab that sample. And then I'll bring it over here. All right. And for A, let's see where it is. There's sample code. Right, so here's output is talking about this. Okay, so comment ignore to start block. So what's scope 1? Boromir created scope 1, Legolas created scope 1. Gandalf never created, so he's undefined. Then we come along into a nested block, so we're now in scope 2. Gandalf exists. Print Gandalf, output is current value 49. Same thing with Boromir. Then we close the block. Right, so when we hit this finish block, Gandalf is destroyed. So it goes back to like we were in the previous state, saying Gandalf is undefined. Yeah, so it was created and existed, but just like here, we'll just use, right? My scope rules are just like C, so we can do what I'm talking about. Right here, if we're trying to say cout. Cout, Gandalf. Gandalf. Right, this doesn't compile because Gandalf is not declared. Go ahead and say, go ahead and put a nested scope. Gandalf equals 5. Right, and we run this, right? It spits out 5. We're good to go. But then if I try to put Gandalf afterwards, right, it says it's not declared in the scope. Same thing, except we don't have a compile language, we have an interpreted language, so we don't know that line 20 has a problem until we get to line 20. Right, so this is finish, and this is start. So anything that's still in scope, int Legolas equals 25, right? So we can print Legolas anywhere in main after we've defined Legolas, whether or not a subscope has come and gone in that time. Now, I wouldn't call it global. It's just that what scope it's in, right? So just like here, main, everything is a local variable. Legolas is a local variable and Gandalf is a local variable. Gandalf is just simply defined in a subscope. Right? It's just same as if this were a loop, right? For int I equals 0, I plus plus. Let's try that again. Listen to I plus plus. All right, if I say int subscope equals 20, and then I do another loop, and let's not make that smaller. While subscope minus minus, and we create another subscope equals 10, cout, whatever another subscope is. And I can't use it here, right? I can't say another subscope equals 0. Right, this will give me an error again saying this is gone because it's not inside the start finish block as it were in our language. Yeah, com is like // Yeah, the Borg language is C-based, I guess is a good analogous language to compare it to. So com would generate output. No, we don't do parentheses in our syntax. Everything is just white space delimiter. Yeah, com is just, right, instead of being a // if I wanted to comment out this output statement, I would do com in our Borg language. No, you don't need to account for tabs. If you're using, single space is fine. So I have a test file that slams everything to the left, so there are no tabs. Everything is single space delimited. If you're just doing string stream, the extraction operator will automatically handle, right, there being one or more white space characters in the file, so you won't have to worry about it. Anyways, by happenstance of using string stream, right, just like we use string stream for program 1 for the reverse Polish. All right, so if you do a get line, you get a line, and then you string stream that line, and you can analyze that line and see what pieces or tokens you'll need from that line to do the program logic. And you get the next line, and then do the same thing again until there are no more lines. If there's no var, it means it's not declaring the variable, it's simply manipulating the variable. That's one of our basic operations. This is the assignment operator. All right, so remember, there are two scenarios for a line of code. Either the first word is a keyword, and if it's not, it's a variable name. All right, so let's do a let's just call it string array parsing sort of thing. Lines equals for x print x seems good. For each string line in lines, string words equals line split. Here in this one, I'm definitely relying on single space characters to be my delimiters here. Otherwise, I'd do it right to make this more intelligent, whatever. Important. So if word sub 0 is one of my keywords, I will just go ahead and write line. This is a declaration statement. And then else if one of my other keywords, print. This is a print statement. Why are you giving me an error? Okay, it's just lag for each. All right, and this is my parser, more or less. Of course, we would need to be a little more intelligent. See, I saw the screen flopping by. So what do we have here? Double linked list? Nope, you don't need to do that. Yes, every entry in the list, each node in the list, the name of the variable, and probably needs scope, depending on which of those two approaches we talked about earlier. The first approach, you want scope. And the reason you want scope in the variable is so you know who to delete when we close the scope. For your submission, you would submit your executable, if you have one, the .cpp file and your .borg file that is your own test file that you use to make sure your program is working. All right, string var name equals word someone. And let's see. Declaration of our name. All right, so declaration of X. All right, so if there's that, and then there's optional, if words length is greater than 2, that means we have var X equals 10 sort of thing. Go ahead and hold that right line. Initialization of our name to var value. So let's get those in there. So we got the var name. Twist the code around a little bit, so we need to get this var value out. All right, so just give me things as a string for the moment. But this would be words sub 3. So if I added another line of code, var y equals 10. sort of thing. Right, initialization of y to the value 10. I would just need to convert that to a non-numeric format. And then these two pieces go into the table. Let's see. Yeah, var is how we create a new node. If there's no var, right? If we just say x equals 20, because right now when we're printing x, it's just 0 garbage, no difference. That's going to fall into our else branch. The first word is not a keyword, and it's a variable. And so at the moment, we'll just go ahead and write line variable operation. And run that. All right, so our last line of code is for operation. I might as well just go ahead and spit out the code, gives us more context. Good for debugging. Spit out the line plus colon, and then what we're doing with it. All right, so we have var x, that's a declaration of x. We have print x, get to our print statement. Var y equals 10, that's our initialization of y to 10, then x equals 20. Here's our variable operation. All right, so here we just need to account for, we also have, x equals, right, x plus y type of thing. So there are two formats for this last branch. It's either 3 tokens or it is 5 tokens, right? We're not doing any reflexiveness, so if words length is 3, we have the one form, otherwise it's the long form, be explicit, say 5, otherwise good to go. So variable assignment, and then lastly, variable arithmetic. So let's add in, I have it there already. All right, so x20 is the assignment situation, and then here's our arithmetic situation where just grab that token, see what it is, do the math. Yeah, you want to run my sample file so that you can see that the output's lining up. And if not, why isn't it lining up? And then your own test file, because that sample file does not exercise everything that the language can do. Okay, let me swing back. Practice test, because I didn't actually have any questions on the memory items. So I just want to make sure that paying attention. All right, locality reference based questions, that's just, short answer, true, false, multiple choice type things. No actual right number. No, there's no number crunching like we can have with other stuff. Right, memory allocation. I guess let's expand this. Right, this is first fit, best fit, worst fit. And memory fragmentations, internal, external, and data fragmentations. Do we have any questions on these areas? Okay, well, that should conclude all the material for the course. Let me double check. I didn't forget anything. Let's check. And all right, garbage collection, compaction, dynamic storage, memory management. All right, covered all that stuff. Hashing. Yep. Graphs, all that good stuff. So you don't have to worry about that for this final. Let's test, but it's on the final. All right, that is the material for the course. All right, like I mentioned earlier, work on program 4 now, right? That's due in a couple days, after which the late penalty starts applying. If you think you have 80% of the program done by Wednesday evening, turn it in at that point and then keep working on any leftovers. Because right, if you wait a week and then right, it was like, okay, you switch over to test and then go back to program 4 and then submit it without having initial submission, you're already in the late penalty territory. You're starting to lose points. But if you have 80% of it by Wednesday, you can get all those points, and then the late part can you just apply to those last 20%. So something partially working, ship it to market, and then start issuing the patches. That's how business works these days. You can almost always expect a day 0 patch to come along with the original install. The advantage of not having to ship things by disk anymore. Because if it still does some of its job, it's still usable. If it's completely useless, there's half of this, half of the other, which way you want to go. But something is all something that's on point is worth more than nothing. Or if you go just submit your tree code, of course, that's not going to be useful because it's not hashing. And just like I was doing here, and I can share this one too, in case you want it. C#, so it's not code relevant, but right, if you're getting stuck on reading from a file, bypass the file, right? So here I just completely bypassed the file. I just made my file as a line of code in the text so I can get to the point where we have the interpreter, which is a chunk of the work, and then the actual hash code, which is the other chunk of the work. Right? So we're getting stuck on just doing an F stream, right? Ping that in Discord so we can get you unstuck on that, because IO is a skill that you hopefully picked up in your C, C++ courses, but of course it's one of the ones that you tend not to use very often, so it's quite understandable that you've developed Rust in an area, but right, C++, read from file versus read text file. All right, C++.com. And that one's right into the file. Switch over here to reading from a file. There we go, F stream. All right, opens the file, gets a line, spits it out. And once you've got that line into your string, then you can go ahead and break it apart and work on it. Okay, if there are any other questions, well, let me check Discord, see what's floating over there. See a bunch of pings. Let's see. What did we get? Let's see. Let's swing back. Well, we'll go ahead and keep posting the general channel for that. Where were we? Not you. Not you. This one. All right, the footprint. I'll just go ahead and put a screenshot in there. Make sure easier to cross-reference. Fill in the footprint. Padding. All right. Is that for the character folding, Eric? All right. So character folding. Let's see. Let's just do more folding examples. Anyways, and I'll just add it to the end here. All right. There's a review section. It says at 5.13 review. All right, so folding. Say our data is just 1, 2, 3, 4. And our fold length is 3. So our first fold, 1, 2, 3. And our second fold is 4. Right, so we need a pad for, so we have left padding gives us 1, 2, 3 and 0, 0, 4, which then equals 127. Right padding 2, 3 and 4, 0, 0, which equals 523. So if we're doing characters, right, character folding, right, so we have our data is A, B, C, D. We're taking our ASCII 65, 66, 67, and we're taking that and we're adding it together since each fold is identical length. Right, so fold length 1. Let me just add it up to whatever that is. It's 240 plus 26, 266, I think. Correct my math if I'm wrong. So if we do the same thing, fold length of 2, right? What we're doing here is we're just taking the values and then applying them together, and whatever that equals to. Where I'm looking for my calculator, that's what I'm doing. 6566 plus 6768. And then adding that together. In the example I did, and then added to the lecture notes, what I was doing, I was just pushing the numbers over by 2 digits because I was thinking of my capital ASCII all being 2 digits, so I just pushed them over and then added them together. Like I'm doing here, but when we're doing it for an odd length, right? So we're doing ABC, right? And we need to pad the data, full length, the left pad, whatever that adds up to being. 6634. Yeah, these are hash functions. There was a question about the hash functions. Yeah, so for the test, it would specify which fold to use, or if it doesn't specify, you could use either one, and then I would put in the answer key the answer to both. So you can do it whichever way. All right, so right pad, same data, but padding it on this side, which then of course changes the math. right? And then there's lots with all these hash functions. There's a lot of different ways we can nuance the data together slightly differently. Right? Just like with when we're looking at MD5s and SHAs, where it's doing ands and ors and XORs and NOTs and all that fun stuff. Just by shifting the operators around a little bit, you change the pattern. The key thing is a given hash function is used for adding the data, and that same exact hash function is used for doing the lookup. Right, and with our character folding here, we're assuming just using the underlying ASCII value. Right, we could also do other translations, right? A is 1, B is 2, C is 3 sort of thing, and then add up the values that way. Right, and the whole idea is the hashing is we're mashing it together. Chop and mix. Any other questions that we want to hit tonight? Still have plenty of time if there's other things we want to look at. Review for the test next week. There are no answers to no questions. Question about program 4, you can message me or you can ask it here. We're here now. It doesn't matter, but the chain is doing the collision handling. So if we had the same code and everyone happened to go to the same list, they happen to go to the same list, that's just what's going to happen. If you wanted to improve the performance of the chain, what you can do is, just like when we have open addressing and a load factor, and we saw when we're looking at the .NET implementation of the hash table, when the table capacity, the occupied cells crossed the load factor threshold, it went ahead and resized the table. So the same thing could be done with chaining as well, where we look at list length. A list crosses a length threshold, so it's like more than 2 nodes long, that it wants to resize the table. So it grows the table from 3 to 5 or 3 to 7 or something like that, so that it can reallocate where the nodes are in the list to keep them shorter. That would be beyond the scope of what we need you for the program for. And the user shouldn't want to know from the if we're just building, if the application is just storing data in a hash table, the user shouldn't care what the hash value is. If the application is showing hash values, then you just output the hash value, and you can show with which ones are collisions just on values alone, which is possible, just unlikely, and which ones are collisions because of them being squeezed into a hash table. Yeah, so for program 4, the collisions are all transparent to the user. All the user cares about is that they can write the program and they can get to the variables that they have access to. And if they write a buggy program by saying print Gandalf when there is no Gandalf, busy fighting a Balrog, they cannot be seen. This is off a separate adventure. Any other questions? All right, good night. We'll see you next week. I'll try to get a couple of, I see at least 4 items for grading for program 4. I'll try to get that before Wednesday in case there's any bugs that I find. And let me know if there's anything else you want. I can find more links and other things for you to check out.